Hey there, chemists. In this lesson, we're going to look at some reactions that involve using amines. We looked at how we synthesize amines in the last few lessons. We're just going to wrap up this unit with a couple of new reactions that involve amines as starting materials. The first one is a familiar reaction. It's the SN2. It's an alkylation, and what I'm actually going to call the over-alkylation. That's a common problem with amines. It's actually already drawn completely on your notes. This is an SN2 showing how ammonia can act as a nucleophile to attack iodoethane. The iodine leaves. You lose an H+, and you would initially get a primary amine. However, this doesn't stop. It happens again. And you get, in this case, a secondary amine, which still has the potential to keep going to give you a tertiary amine, and ultimately a tetraalkyl ammonium salt with 4 carbon groups attached to that little nitrogen that used to be just an ammonia. So this is not a good way to make an amine because it usually continues to go all the way to the ammonium. Now, a couple of chemists have exploited this, and we're going to look at some reactions that involve using those alkyl ammonium salts. First is called the Hofmann elimination. This is developed quite a while ago from the late 1800s, and this was after August Wilhelm von Hofmann, a German chemist who first showed us this reaction using amines with alkyl halides like iodomethane. The reaction is very straightforward. It starts with using the SN2 of something like iodomethane to give you a tetraalkyl ammonium salt. Now, how many iodomethanes do we react? Well, the nitrogen can occupy up to 4 carbon sites. 1 is already there, so we can have 3 more on this nitrogen to give a tetraalkyl ammonium salt that looks like that. What's the point of this? Well, we can actually use this with base. That's what silver oxide and water is doing in this reaction. And this will undergo an E2 elimination where we lose a beta hydrogen and create an alkene. That's the point of the Hofmann elimination. What makes this unique is you get the non-Zaitsev. Remember, last semester we looked at eliminations like E2s, and we would lose a beta hydrogen. Alpha is the carbon directly attached to the nitrogen, so beta is 1 more past that. The E2s that were Zaitsev would lose beta hydrogens where there were fewer beta hydrogens to give you a more substituted alkene. This will do the opposite. You will lose a beta hydrogen where there are more abundant beta hydrogens and get the less substituted alkene, what we call the non-Zaitsev alkene, also called the Hofmann alkene as a result of this. So I'll draw out that beta hydrogen. It's right there. The base will take away an H. The CH bond breaks. You form a new carbon-carbon pi bond between the alpha and the beta bond, and the nitrogen actually acts as a leaving group. So you get your alkene, in this case a less substituted butene, plus just a trimethylamine molecule in the end. So it's just a way of using tetraalkyl ammonium salts for a synthetically useful reaction. There's a very similar one that came about 50 years later called the Cope elimination. It also involves an E2 to make a non-Zaitsev alkene, but it's very clever in that it works with an intramolecular version of an E2. So what I'd like you to do is take a look at this reaction scheme, which is the complete mechanism on your notes, just missing the curved arrows. So hit pause and see if you can add curved arrows to this mechanism for the Cope elimination. Okay, if you've done so, the first arrow is just the nitrogen attacking peroxide. Peroxide is an electrophilic source of oxygen. It breaks the oxygen-oxygen single bond, and you get what looks like a hydroxyl ammonium. The hydroxide that just left will take away that H, and you get this ylide with an oxygen anion and a nitrogen cation directly attached to each other. This is called an N-oxide. It's the key intermediate in the Cope elimination. But then to do the elimination, you simply heat this up and you lose a beta hydrogen. You will also lose a beta hydrogen from the site where there are more of them. So I'm going to draw in the beta hydrogen that's more abundant and then show the curved arrows where The intramolecular E2 is the oxygen anion takes the H, the CH bond breaks and forms a carbon-carbon pi bond, and then the carbon-nitrogen bond breaks and you get a byproduct, which is called a hydroxyl amine. But the main product is the non-Zaitsev alkene, just like in the Hofmann elimination. So there's a couple of examples down below that are a mixture of Hofmann and Cope eliminations, numbers 39 and 40. So I'd like you to once again hit pause and see if you can try these 4 questions that are eliminations of amines via ammonium salts. Okay, if you've done that, let's see. The first one is a Hofmann. Looking at the starting material, I've got 1 carbon group attached, so I can have 3 methyls attached to the nitrogen, and you'll get a tetraalkyl ammonium that looks like that. The base, drawn way over here, the silver oxide is just acting as a base. We'll take away a beta hydrogen from the site where there are more of them. We'll draw an arrow from the base, breaking the CH bond, and then losing the triethylamine. Your product is just pentene in this case. That's your main alkene product. For the Cope elimination right below it, we first form the N-oxide, which is a nitrogen still with 2 methyls on it, and then an oxygen anion directly attached. And it's that oxygen anion that acts as the intramolecular base. So here I got to figure out which beta position loses the hydrogen. If it's hard to see, just go ahead and label everything. The alpha position is the carbon directly attached to the nitrogen. And then anything attached to the alpha position is a beta carbon. You just keep going down the Greek alphabet. You're looking for the one that has the most number of hydrogens. That's this one up here, the methyl. So if I draw out that hydrogen, that means the oxygen is going to take that H, the CH bond breaks to form a carbon-carbon bond, and the carbon-nitrogen bond breaks, and this one gives you an exocyclic methylene. You will get methylene cyclopentane as your product, and then the hydroxylamine that we saw before. And then we have another Hofmann elimination. This one already has 2 carbon groups attached to the nitrogen, so you're only going to use 2 of the methyl iodides, of the iodomethanes. So your intermediate has a 5-membered ring and a positively charged nitrogen with 2 methyls on it, and then a methyl sticking out on the side. The base is going to take away a hydrogen from the beta spot that has the most abundant H. That's the methyl. So I'll draw an arrow from the base to the H. The CH bond breaks. I make a CC double bond. The carbon-nitrogen bond breaks. And this is an interesting example where the leaving group stays attached to the original molecule, and you get an alkene that looks like this, with the dimethylamino group still attached to the rest of the molecule because it was there in the first place. It's possible this continues and does a second elimination where you would lose this group and put an alkene right there and get a diene. That's certainly possible, but we'll just draw the product of the first elimination. The last one I asked you to do before we hit pause is this challenge question, which looks tougher than it is. It's just a 3-dimensional molecule. The first part involves putting just 1 iodomethane on the nitrogen group. You have this bicyclic molecule. It's a tertiary amine, and you'll add 1 methyl, giving that nitrogen a positive charge. Now, under the Hofmann elimination, we lose a beta hydrogen. Where are the beta hydrogens? Well, there's a beta carbon here, here, and here, which, if you look at this molecule by symmetry, they're all exactly the same. So any of those positions are viable for losing a hydrogen. They're all the same, it turns out. So the basic conditions will take away the H. The CH bond breaks, you form a CC pi bond. It breaks your carbon-nitrogen bond, and your product initially looks exactly the same, except we change what's changed. And that gives us an alkene out here with our methyl, no more positive charges. Now, that is the right product. We just broke that carbon-nitrogen bond right there. It's no longer there. I just put a dotted line where it used to be, and we get a new alkene between the alpha and beta carbon in the original material. It might be easier to look at this molecule if we redraw it. Let's redraw it. This is just a 6-membered ring with a vinyl sticking off of the ring opposite where the nitrogen is. So I'll draw a 6-membered ring with a nitrogen, has a methyl on it, and then there's a vinyl attached on the opposite side of the ring. That's your product of that elimination. So those are just some interesting applications of the elimination reactions from ammonium salts. I'll just end this video with how we can look at the basicity of amines. Amines are bases before they do almost anything else. So just to remind you of a couple of things you learned in the earlier parts of this course, we can rank basicity by looking at the conjugate acid. So I want you to hit pause one more time and figure out what the conjugate acid of these 4 bases would look like. They're all pyridines. They're just nitrogens inside a benzene, and those can pick up an H. And after you draw those conjugate acids, think about the stability of those conjugate acids. Whoever's the most stable would come from the most basic pyridine. Hit pause and try that now. Okay, well, if you drew the conjugate acids, the conjugate acid is just what it looks like with an extra H, resulting in a plus charge on the nitrogen. So you make ammoniums, which is really the theme of this lesson. So first I'll simply turn all of these into the conjugate acid by making them ammoniums, or really pyridiniums would be a better way of describing them. Who's the most stable? It's the first one. The first one has a lone pair on that nitrogen atom up there in the dimethylamino group, and it can donate that pair of electrons into the ring and perfectly stabilize that pyridinium ion. So you have, among others, this very significant resonance contributor that looks like this, where I've sent that positive charge all the way up to the dimethylamino group. That's just one resonance contributor, but it's a pretty good one. There's no other molecule that has quite as good of a donation to this. If you try to do it with the methoxy, you can't ever get the electron pair to satisfy that positive charge. It looks like you could at first, but remember, we'd violate the octet if I tried to do that arrow pushing right there. So that's not going to happen. You're not going to violate the octet. The regular pyridinium ion is sort of our baseline. And then right next to it, we have this ester attached. Remember what esters look like. A CO2 methyl, that's a carbon with a doubly bonded oxygen, and then an O methyl directly attached. That's an electron withdrawing group. If anything, this is pulling electron density out of the ring, destabilizing the plus charge. That probably suggests that this is the least stable conjugate acid, meaning this is the least basic pyridine in the beginning. So let's just write a little bit about what we have here. The first one, the first molecule is the most basic because it has the most stable conjugate acid. Remember, stability ranks with being not very reactive. So if something becomes something that's very stable, that means its counterpart was very reactive, aka strong. So the most basic thing was the least stable base, turning into the most stable conjugate acid. So that's just a review of how amines are basic and how we can rank basicity, and then a couple of applications of forming positively charged nitrogens, aka ammoniums, to make alkenes.